Hello there, everybody. Welcome to another MCAT ACE lecture. And in today's lecture, we're going to be covering the general chemistry topic of mass, moles, and molecules. So to give you an overview of what we hope to accomplish in this lecture here, the atomic structure of an atom is first going to be brought up. Just a basic review as far as protons, neutrons, and electrons and how they are assembled. And in particular for this lecture, because we're going to be talking about mass, we need to discuss how we determine the mass of a given atom when we're looking at protons and neutrons. So from there, we'll start discussing the atomic mass unit, which is abbreviated AMU. It's a very common unit that is utilized when people first start learning chemistry, and then we tend to use molar mass as we move along and start talking about grams per mole. The AMU is sort of upgraded and upscaled because most of the time we're dealing with things on a macroscopic level. We're talking about measuring out milligrams or grams, not individual atoms or molecules, which is more relevant to the AMU, the atomic mass unit. So we want to discuss the atomic masses that we find on the periodic table, because when you take a look at an atom and add up the protons and neutrons, you would expect a very straightforward mass, assuming a proton and a neutron is each one AMU. And then sometimes when you get to the periodic table, you don't see these whole nice numbers. You'll see something like 63.5 for copper. And so that sort of implies that you have half a unit, either half a proton or half a neutron that's there. Most of the time it comes out that it looks like it's half a neutron. And when that occurs, you need to understand where that's coming from. That's really coming from the fact that there are multiple isotopes of copper or carbon or nitrogen or any of these compounds. There's usually multiple isotopes, and the weight or the mass that comes on the periodic table is a result of these isotopes and their average based on their natural abundance. So we'll talk about that for a few minutes and take a look at isotopes and use an example there. So then we're going to head into talking about the mole. And the mole is the central unit of chemistry. We always deal in moles when we're working with chemistry. And then from moles we can convert to atoms or molecules. We can convert to grams. But moles is the center unit. So we want to define what is a mole. You can be certain that Avogadro's number is going to come up when we start talking about this section. And then finally, we're going to talk about determining molar mass. So what happens once I go past a single atom, right? How do I find the mass of water or glucose or things like that? And then finally, determining the moles or the atoms in a molecule. So this would be sort of taking everything together, where if I have, let's say, 20 grams of water, and I want to know how many individual water molecules I would find in 20 grams of water, that's the type of calculation we're talking about doing there. So I will mention, while this particular lecture and subject is not stoichiometry, this is the prelude to stoichiometry. We're going to be starting to talk about stoichiometry very soon after this lecture, because then you're getting into balancing equations, which can lead to limiting reactants and percent yields. And then we can start talking about concentration and molarity. We can start talking about titrations, which require balanced equations. So all of this is sort of your pregame, or your preparing, your training for stoichiometry. That's what this lesson is really going to be about. But I don't want to classify it exactly as stoichiometry, because stoichiometry really has to do with the ratios when we start looking at balancing equations and how many moles of one compound give us how many moles of another compound in those balanced equations. So different subject for a different lecture, but keep in the back of your mind that this is where we're headed with this subject. We're going to start talking about stoichiometry eventually. So with all that being said, let's go ahead and let's get started. And I'm going to leave this up here right now. I'm going to mention that you would do very well to have a periodic table in front of you during this lecture. Probably for most lectures with any chemistry topic, you're going to want a periodic table. But because I'm going to be going back and forth, we're going to be doing calculations, so I would also suggest you get a calculator before we start. And I also want to mention the periodic table here. This is a very generic, basic periodic table. You can get some that go out to 2 decimal places. That's probably the most common. And then you can get some real nice ones that go out to 4 decimal places. So a lot of these figures right here, these numbers, the masses are rounded off when we're dealing with the 1 decimal point. But this should suit our purposes because what we're really going to be dealing with or talking about here is preparing you for the MCAT. And in the MCAT, they're not going to give you some very advanced, long run-on periodic table with all of these detailed masses. You're probably going to get something that looks more along the lines of this right here. So using something like this should be absolutely fine for our purposes. But again, because I'm going to be going back and forth and scrolling back and forth, it's probably a good idea that you have one, especially when you want to practice, because at some point I'll have to clear this off to bring up the practice questions. You're going to want your own periodic table and calculator as you're working through that and setting that up. So just a sort of a mini warning about that now so that you can go get that stuff if you need it before you continue. So let's go ahead and let's start discussing down here the general structure of an atom, because that's where we're really going to start here. Now, this is not going to be in huge detail. We're not going to start talking about atomic orbitals and shapes and, p shells versus d shells and all that. That's more for bonding or quantum mechanics lectures. We just want a very basic understanding of an atom, and that is that we have the nucleus at the center of the atom, and inside of the nucleus is where the protons and where the not the electrons, absolutely not, and the neutrons are going to reside. That's where your protons and neutrons reside, is inside the nucleus. Now, keep in mind, the nucleus is a very, very small unit in comparison to what we would call the electron cloud or the electron shells, whatever you want to call them, the orbitals. There's kind of this classic representation of the atom where you draw these orbitals like this, right? And you've got the electrons that are sort of orbiting around. And that's fine for a generic idea, but this is very misrepresented here because our orbitals, we know they take up different shapes. So you have s orbitals and p orbitals, and they all have different, electron distribution statistic parameters. So the main concept that we want to sort of gather here is that the protons and the neutrons are in the nucleus, and these are going to contribute to mass. So this is going to contribute approximately 1 AMU, and so is the neutron, approximately 1 AMU. Right? Now the electron would not contribute any significant AMU. Now, some students get confused here because it's really about 5 times 10 to the 4th in terms of AMU contribution, right? When you talk about something that small, the example that I like to give is if you're weighing out a gram of some substance or compound, and then you add a tenth, not even 1, but a tenth of a milligram, all right? So a milligram is 1,000th of a gram. So you're talking about you need 1,000 milligrams to make up 1 gram. So if I'm weighing out 1 gram, and then I'm talking about taking a tenth of a milligram, so a tenth of 1,000th, is that really going to contribute significantly to the 1 gram that I have there? And the answer would be no. Then I'm talking about if I added that, I would have 1.00001 grams, and you round it and you say, oh, it's a gram, right? So it's the same concept here with the electrons. The electrons are considered to have mass. So some students think, oh, electrons are just energy. That's not true. Electrons, while they can certainly behave on the electromagnetic spectrum in terms of, electromagnetic energy coming in and exciting electrons, and they do have charge associated with them, electrons do have mass. It's just very insignificant in comparison to that of the protons and the neutrons. So protons and neutrons are where we gather or focus our efforts in terms of the mass of a given atom. So every proton is going to lead to 1 AMU, and we represent atoms by using their atomic number, right? And the atomic number, I'll circle 102 up here because it's on the screen. That's the atomic number right there, right? So all of these would be atomic numbers, and atomic numbers are the way that we identify an element. It gives the element its identity, its chemical properties. It's basically its identity is what it's leading to. So it's not appropriate, especially when we start talking about isotopes, to talk about changing the number of protons because what you're doing at that point, you're changing the identity of the element. Now, sometimes it is true, it's possible that an element can go from one set of protons to a different number of protons, but when that occurs, that's a type of radioactive decay, and the element will actually change its identity at that point. All right? So radon can eventually decay into lead, and that's why we have radon testing whenever you're talking about, you know, buying a house or something like that. If there's a section that's in the basement or that's underground, they'll do radon testing, and that's because radon, if you breathe it in, it's heavier than air. It'll just sit in your lungs over time, and it will slowly, very slowly, radioactively decay into lead. And when it loses the protons that we're talking about with that radioactive decay, it becomes a new element. It's not radon with some different number of protons. It's now a completely new element. All right? So the point here, protons are going to, the number of protons will be associated with the atomic number, and the number of protons is what we use to identify an element itself. Now, the number of neutrons can vary. So when we get to neutrons, neutrons do not have a charge with them, whereas protons have a positive charge, electrons have a negative charge. Neutrons do contribute mass. They hang out in the nucleus, right? And what we do is we say, all right, if we want to find the atomic mass, or the atomic mass units, okay, which we represent with AMU, we can find that, and sometimes this right here will be represented with A, okay, but we can find that by taking the protons plus the neutrons. So if I sum those up, assuming they're 1 AMU apiece, I will find the atomic mass. It's really the atomic mass. The unit is one of these individual. So every proton would be 1 AMU, every neutron would be 1 AMU. Okay, sometimes the protons, the atomic number is abbreviated with Z, and then you can find the neutrons. So this is the same equation as above, but sometimes you'll see Z and A used as those values that get plugged in there. So you'll have an element, like element X, I'm just using a general example here, and we'll say, okay, the mass of element X, and then its atomic number. So for instance, carbon 12, meaning the mass is 12, and carbon always has 6 protons. Whereas I could also have carbon 13 with 6 protons, and carbon 14, that's the carbon used with radio dating. When we have carbon dating, you're looking at the radioactive decay of carbon 14. And again, 6 down here. So look, 6, right? The atomic number, right? The number of protons is the same. A carbon is a carbon is a carbon, but we can have different values up here as far as the mass is concerned by additional neutrons, right? So in this case, if we were to look at this, just doing some basic math here, we would say if this is 12 for the mass, I would say 12 minus, and then, I'm sorry, not there. I would say 12 is equal to 6 plus the number of neutrons. So here's the atomic mass, and here is the atomic number, the number of protons. So I solve that, and then I would find that n equals 6. I was actually getting ready to write that out as solving for the neutrons, which would be the atomic mass, A minus Z. All right, but you could do that again for 13. So I could say carbon 13 is going to be equal to 6 plus N. So in that case, there's 7 neutrons in a carbon 13. And then in carbon 14, I can say that I've got 6 plus N. So in that case, I have 8 neutrons that are hanging out in carbon 14. So these right here are known as isotopes. Okay, and do not confuse that with isomers, because isomers talk about when we get to compounds and we take the same number of atoms and arrange them in a different format. That's an isomer. An isotope is talking about a set of atoms that are identical in terms of their element, right, their number of protons, but they differ in the number of neutrons. So we get different masses because neutrons also contribute AMUs when we're taking a look at that. So that's a basic rundown of this. All right, now, as I was saying before, if we come up and keep this equation in mind, all right, if we come up and we take a look, One of the ones I mentioned earlier that I usually like to use with students, although there's lots of good examples, is with copper. So if I take a look at copper here, copper is element 29. That means there would be 29 protons associated with it, and it has a mass of 63.5. So if I take a look at this, all right, and I come back to my equation, I would say, all right, well, if I'm looking at 63.5, right, that's going to be equal to, and then you come up, you say 29, because that's the number of protons, right, plus N. And so if I get ready to solve this, what's going to happen? I'm going to take 63.5 minus 29, and I'm going to get a fraction as my number. So if you're confused by what I mean when I say this, all you have to do is run 63.5 minus 29, and you'll find out that N is equal to 34.5. Well, that doesn't make a whole lot of sense. Okay, there's a point there. Let's emphasize that. That doesn't make a whole lot of sense because a neutron is an individual unit that comes as a whole number when I'm dealing with atoms. I cannot splice neutrons apart and then tell an atom that it can have half of a neutron in its nucleus. That doesn't work. So when I look at this, this is kind of puzzling where we say, well, I don't really understand why we get 34.5 neutrons following the example we were setting forward earlier. All right, now, usually when I ask this in class, the first answer that most people like to state is, it's because of the electrons. We've been neglecting them. They've been building up. Copper has quite a number of electrons with it. All right, it would have 29 if it was in its neutral state. And so they say all of those pile up, and then all of a sudden you're going to get that half of an AMU. And that is not the correct answer. While you may start to very slowly creep up, right, you're still adding additional protons and neutrons as you're climbing up the periodic table. So it's not like the electrons are going to, the ratio is staying the same. They're not going to catch up to a point where they're really starting to significantly affect that to a great degree. So the answer here is the isotopes. There is more than one type of copper, and again, most atoms have multiple types of isotopes. There is what we would call copper 63. And again, this would be 29. And there is also a copper 65, 29. Right? Now, if I take a look at this, the mass that I get is really going to be a mass from the weighted averages of the natural abundance of these two isotopes. And we'll talk about what that means mathematically in a moment. But just take a look. If I have copper 63, and I have copper 65 in nature, which one do you think is more prevalent if both of these are weighted? Think about like a weighted grade, right? If both of these averages are weighted in terms of how much they contribute to the average atomic mass, right? And the answer is the one that should be more prevalent is copper 63, because I find a number of 63.5 that's much closer to 63 than it is to 65. So that's not to say that I don't have any copper 65. There's actually going to be quite a bit of copper 65 that I can find. It means that in comparison to copper 65, I find a lot more copper 63 sitting out in the natural abundant universe. All right, so when I take a look at this, if I come down, it turns out, now these values, I'm rounding them off here. So you may see examples if you go online and you look online that are a little more detailed than this. But for the purpose of what we're using with our periodic table, I'm rounding this off. So copper 63, the proper weight for it, because we're estimating that it's about 1 AMU, which is a pretty good estimate per proton and neutron. The correct value here is, it really weighs 62.9. It's almost 63. Right? And then the other copper 65, turns out that that value, similar to the other one, is 64.9. Right? Now these values continue if you were to run the decimals all the way out, but this is good enough for the example we want to use here. So we said that there should be more copper 63 than we're seeing in terms of copper 65. So what I can do here is I can give you the averages. I would say this one, it turns out, is about 69.09%. And then the copper 65 is going to be the remaining amount, and that's about 30.91%. Okay, those are the two major coppers that we come across. So what I would do at this point is I would say, all right, now copper 63 is 62.9 in terms of its AMU, and I will multiply that times the natural abundance of copper 63. Now you do this as a decimal, so it would be 0.6909. That's coming from this value right here, the 69.09%. Right? And then in addition to that, I need to be right, because this is going to take about 70% of that value. So I need to accomplish the full mass by adding in the other 30%. So I would say 64.9, right, times, and then I would do this one also as a decimal. 91. That looks like another decimal in there. 91. All right, so there you go with that. Now, if you plug this into a calculator, and I encourage you to pause it for a moment and run this through, see what value you get. So go ahead and run that through a calculator. All right, so hopefully the answer you came out with was 63.5, and that is the mass that we find up on the periodic table, 63.5 for the copper. So that's where that value is coming from. And we understand that it's not really half a neutron, it's the weighted masses that are coming together to give us an average mass in terms of the number of copper 63 we would find in nature and the copper 65 we would find in nature. Because if I took a giant sample of copper, about 70% of that copper sample would be copper 63, and the remaining 30% or so would be copper 65. So how do you come up with a appropriate mass? Which one do we use? We take the average weighted value of both of those masses, and that's going to be what we end up using from the periodic table. Okay, so if we come back up here, we've taken a talk about atomic structure. We've talked about the atomic mass unit, which is a proton or neutron value. And we've now discussed the atomic mass on the periodic table and how isotopes play a significant role in that. So the next thing we're going to talk about here is the mole and molar mass. All right, so to start that off, I want to bring up the idea of the atomic mass unit again while I'm just clearing the board here. So the atomic mass unit, or the AMU, comes from protons and neutrons. And the way that we define an AMU, because that's still kind of a little bit nebulous as far as its definition, there is an actual definition, which is that an AMU is going to be exactly 1/12 the mass of a carbon-12 atom. So if you come up and you look, here's carbon. Carbon is 12.0. All right, so we define an AMU as 1/12. Meaning if it's 12, it would be exactly 1, right? 1/12 the mass of a carbon-12 atom. And we say carbon-12 because there is carbon-13 and carbon-14 and so on and so forth, right? So that's the idea of the atomic mass unit. So bringing up my pen here, now that I deleted, the AMU, the atomic mass unit, is equal to 1/12 a carbon-12 atom. That's how we define an AMU. So we know that the table uses the average AMUs from the different isotopes. Okay, so then we start to switch over, and most people that you come across are going to start talking about molar mass, and this term is important here, molar, because atomic mass unit is on the atomic level, whereas molar mass is going to be similar to the atomic mass, but when we talk about it, it's going to be on a molar level. So we're going to start scaling it up. And I'll tell you what I mean here in a minute when you think about it. All right, the molar mass is going to be the mass in grams. Now you could certainly convert it to milligrams or kilograms or something like that, but it'll be the mass in grams in 1 mole. And we will define what a mole is here in just a minute because we're getting ready to talk about moles. But it is the mass in grams in 1 mole of units. And if that's kind of confusing at the moment, again, we'll define mole here in just a second. All right, so mole, now we need to discuss what a mole is. Mole is going to be the number of atoms. Now think about the atomic mass unit. It's going to be similar. It's the number of atoms in 12 grams of a carbon-12 isotope. All right, so we're using carbon-12 to base a lot of these definitions. And we can define a mole as the number of carbon atoms found in 12 grams of C12 isotope. So that's going to be a lot. Think about 12 grams. Something that weighs 12 grams, you can think about a small balance you might have in a kitchen or in a lab. You can physically measure out 12 grams. You can hold 12 grams worth of material in your hand very readily, and you can see it. All right, now think about how small atoms are. It doesn't make sense that 12 atoms would weigh 12 grams or anywhere close to that, because we were talking up here about 1/12, and AMU is 1/12 of a carbon-12 atom. So when we're talking about this, this is getting scaled up. We're saying 12 grams of a C12 isotope gives us how many atoms? And it turns out that that number of atoms is going to be Avogadro's number. So this is a value that is very well known. It's one that you will need to know for the MCAT. Okay, Avogadro's number, or at least you need to know how to utilize it. I'm going to be rounding here, so this really does continue on, and there's a 1,415 that comes after the 22 there. But this is Avogadro's well-known number. And it is 6.022 times 10 to the 23rd. So the 10 to the 23rd, that placeholder means that I continue zeros. There's going to be 23 spaces, right? So the first three would be 0, 2, 2. And then after that, there's another additional 20 zeros that come after that. They wouldn't really be zeros. Again, I'm slicing this off and I'm rounding. But there's a massive, huge number of atoms in a very small sample as far as grams go. All right. Now, some students get confused when we talk about the concept of a mole and Avogadro's number, because Avogadro's number is a set amount. So a mole is a set amount of material. A mole is always the number of atoms in 12 grams of carbon-12, and that turns out to be this number, Avogadro's number. So the best thing that I can equate this to, if you're kind of struggling to understand this, is think of a term that always has the same meaning as far as numbers go. So for instance, a good example would be a dozen. A dozen, if I tell you a dozen, that holds the same meaning no matter what I'm talking about. So I could be talking about a dozen computers, a dozen bowling balls, a dozen donuts, a dozen pencils, a dozen students, a dozen cars, a dozen cats. It doesn't matter. A dozen is always referring to 12. It's the same thing. If I talk about a mole, I can have a mole of water. I could have a mole of carbon. I could have a mole of cars. Okay, that would be an enormous number of cars, right? Probably couldn't even fill up the entire planet. It would be too much. However, whenever we're dealing with a mole, it's always the same amount, and that amount is 6.022 times 10 to the 23rd, and this is units, because again, just like I was saying, pencils, donuts, cats, whatever, those are all different units. They're different things when I'm talking about the dozen. So when we get to Avogadro's number, a lot of students think it's atoms, and that can be true. It can be atoms, but it can also be many other particles or units. It could be the number of water molecules. It could be the number of carbon atoms. So water is H2O. That's 3 atoms per water molecule, but I could still have a mole of water molecules. Okay? Now if there are 2 hydrogen atoms in every water molecule, and I have a mole of water molecules, then I must have 2 moles of hydrogen atoms, right? So again, if you get confused with that, go back to the example of a dozen. Let's say that I have a dozen donuts, right? And each of those donuts has a dozen sprinkles. So I have a dozen donuts, but then I would have 12 dozen sprinkles, because every donut contains a dozen sprinkles. So it's the same concept when I'm talking about moles and then I can say the molecules, the atoms, etc. And we'll take a look at some math with some of these examples that we want to talk about here. So one of the first things that we're going to start doing now that we have a grasp on moles and molar mass and everything like that, okay, and again, this is grams per mole is the unit when we start talking about molar mass. We want to start calculating the molar mass of some compounds. So I'm going to give a couple examples here, right? And ideally you want to pause and work through this as you're going through. So the molecules that I'm going to give you to work with will be water, because we keep talking about that, so that's a pretty common example, water, okay, and then we will have glucose, C6H12O6, and then in addition to that, let's do acetic acid, which would be CH3CO2H, and don't forget that extra H that's at the end there, right? So some of these are organic type of compounds with carbons. So the idea is find the molar mass, find the grams per mole, and this value comes from the periodic table. You want to add up what you're going to be working with here. So again, you want a periodic table in front of you. We'll walk through the first one here, and then you should try the other two for yourself. So for H2O, I come up and I see that hydrogen has 1.0 and oxygen is 16.0. All right. Now again, if you have a periodic table with more decimal points, you may get a more specific answer when you're working with this. So what I would do is I would say there are two hydrogens. The hydrogens are going to be 1.0 apiece times 2 plus then I need the oxygen. The oxygen is going to be 16.0. And if I add those together, I get 2.0 plus 16.0. So the molar mass of water is 18.0 grams per mole. So what does that mean? That means that if I had 6.022 times 10 to the 23rd water molecules, and I put them on a scale, they would weigh 18 grams. There's 18 grams in 1 mole of water. That's what it would turn out to be. So 1 mole of water molecules would turn out to be 18 grams. All right, so pause the video. Try this for C6H12O6, which is glucose, the sugar molecule, and try this for acetic acid, which is CH3CO2H. And you pause it and come back in a minute and we will work through these. All right, so hopefully everybody had a chance to work on this. The first one here, carbon, if you look at your table, should be 12.0. Again, if you have a more specific table, it might be 12.01. You might have some extended decimals outside of this. All right, and then hydrogen is going to be 1, like the previous example. Now in this case, we have 12 of them. And then finally, the oxygen, I have 6 of them, so I'm going to do 16.0, right, times 6. And so if I sum all of these up, and I do the proper multiplication inside the parentheses there and distribute them, I'm going to end up with 180 grams per mole. So you should have obtained something very similar to this, very, very close. Again, your decimal might be slightly different, right? There's a 0.0 there. Your decimal might be slightly different based on the periodic table you're using, but I think I've announced that a couple times now, so you should be okay with that and aware of that. All right, so for the last one here, we want to start with carbon. So again, carbon was 12.0, and I take a look, I can find 2 carbons here, so I need to make sure I multiply that by 2. Plus, how many hydrogens do I have? Well, I've got the CH3, so that would be 3 hydrogens, and then that last hydrogen there on the carboxylic acid is going to make it 4. So I have 1.0 times 4. And then finally, I need to make sure that I add in the oxygens, and I've got 2 oxygens there, so 16.0 times 2 oxygens. And if you solve that and you add all of that up together, you should get approximately 60 grams per mole. All right, so this is how this works. This is how you find your molar mass. And your molar mass can then be used to find moles, and you could also use Avogadro's number in order to find specific atoms or molecules or things like that. So if we come back up here and we take a look, all right, we've now discussed mole and molar mass. We know how to determine molar mass. We go to the table and we pick out the values that we're looking at, and we sum them all up, multiplied by the number of atoms that are there. And then finally, we could use Avogadro's number to convert mathematically and find atoms, molecules, something like that. So that's where we're going to be heading next, is determining the final part here, determining moles and atoms and or molecules. And again, this is getting ready to start working with the math for stoichiometry as we start converting mole to mole ratios, limiting reactants. That's what we're prepping ourselves for here. All right, so what I'm going to do, I'm going to clear off the periodic table because I need a little room to work here. So again, if you don't have one, now's the time. You need to pause this and go get one that you can work with. So I'm going to clear this off. I'm going to bring up some questions here, and we can practice these questions. These can basically be associated as the questions that you are going to practice for MCAT sort of stuff. Again, most of these would be multiple choice, so I can at the end throw up a few more multiple choice ones just to make sure that you're comfortable with this. But overall, this is the type of math we want to be doing. So let me go ahead and delete this, and then I will bring up the questions. Okay, so here are the questions. The multiple choice questions will be very similar in terms of the math that's based off this, and I'll probably throw one or two theory questions in just to make sure that we understand that. So, how many grams of water are found in 2.69 moles of water? How many moles of glucose are in 15 grams of glucose? And then down here, how many grams of acetic acid are in 3.21 times 10 to the 23rd molecules of acetic acid? Now, I did keep these problems in the context of the molar masses that we just found. So you should have some of your work done for you already, but your job is to solve each of these problems and find the correct answer. So go ahead and work through these. Again, how many grams of water are found in 2.69 moles of water? How many moles of glucose are in 15 grams of glucose? How many grams of acetic acid are in 3.21 times 10 to the 23rd molecules of acetic acid? So you want to try to solve these using some multiplication and division and figure out what the correct answers would be. All right? So pause the video, work on these, and then come back after you think you have the answers. All right, so hopefully everybody had a chance to work on these. I'm going to set this up. Now, the periodic table I have in front of myself here, now that the one up here is deleted, uses 2 decimal places as I'm working with this. So the values that I'm going to be using are going to be coming from there. So I just want people to realize if your last decimal point is off by a little bit, that it could be based on those values. All right? So in order to do the first one, we know that we have 2.69 moles of water. And then the question is, how many grams is that? So if I have 2.69 moles of water, some people will set this up using multiplication. I like to use what I call canceling tables. So I put this on top, and then I say, all right, well, 1 mole, which we will often abbreviate MOL, 1 mole of water is going to be 18. Now, it was 0.0. I have 0.02 from my periodic table that I'm currently using in my organic chemistry textbook in front of me. All right, but it's 18 approximately grams of water for every 1 mole of water. That's the first molar mass that we solved previously. So mole and mole will drop out, and if I multiply these two values together, I get 48.5 grams of water. So hopefully everybody was able to come up with that value or something very, very close or similar to that value when they were working through this. Right? So the next problem is sort of working the opposite of that, because it's giving you the grams and it wants the moles. So you always want to start these problems out with what you're given. You have 15 grams of glucose. Okay, so I'll just abbreviate this here. H12O6. Use the formula. Now, in this case, I want to use the grams in order to convert into moles here. And the molar mass for the glucose, based on the periodic table I have, is 180. Now notice it goes on the bottom this time because it's grams in every 1 mole. All right, so for every 1 mole of C6H12O6, there is exactly 180.18 grams of C6H12O6. This larger number should be associated with the grams at all times. So grams and grams. Okay. If I take 15 and I divide 180.18, then what I should end up with, what you should get, is something along the lines of this. Again, your last decimal place might be slightly off depending on what value you plugged in right here. All right, so that's the number of moles of glucose that would be in 15 grams of glucose. And then I say how many grams of acetic acid are in 3.21 times 10 to the 23rd molecules of acetic acid. So this is probably out of the bunch the one that would require the most conversion. So I'm going to start with my 3.21 times 10 to the 23rd molecules. And molecules of CH3, CO2H. It's a very long portion there. All right, so now you cannot jump directly into grams from molecules. You're going to need to go to mole, because mole is the intermediate unit that basically will allow you to jump to anything else. So I have to say, in order to get to 1 mole of the CO2H, this is where you need Avogadro's number, because 1 mole of acetic acid will contain exactly 6.022 times 10 to the 23rd of these molecules. Okay, for the sake of space, I'm not going to write out the word molecules here because I still need more space over here. So when I'm done with that, the molecules and the molecules would cancel out to give me moles. But this question wants to know how many grams of acetic acid. So if I continue forward from there, I would say 60.06 grams in every 1 mole. Again, for the sake of space, I'm not going to write the unit of acetic acid there, but you should follow this with CH3CO2H if you're keeping track of your units. And when you finish all of that, you should come out to 32 grams of acetic acid are found. So what that means is that if I were to count out 3.21 times 10 to the 23rd acetic acid molecules, they should weigh out to 32 grams if I were to put them on a scale. All right, so that is some of the math involved in these conversions when we're working with them. So what I'm going to do next, I'm going to bring up some multiple choice questions that I've created. Again, these particular questions are going to be slightly easier than what you might find on the MCAT, so I just want to give you a reminder for that. Now, when you get to some of the practice problems outside of these videos, when you go to the question bank and you're practicing with ACE MCAT, you need to remember that some of those questions may be very difficult in comparison to these, and that's because we're training you and getting you ready for the MCAT itself. A lot of the MCAT questions may use some of this stuff, like you need a molar mass or you need to know how to do moles and molecules, but they may put it in the context of a balanced equation or concentration. So they might say, you know, how many chlorine atoms or chloride ions are you going to find if you dissolve this much sodium chloride in this much water? And you need to have this background first before you can go and tackle something like solutions and concentration and the moles in that amount of concentration for something like that. All right, so let me clear this off, and then I will bring up some multiple choice questions, and then we will recap and review what we discussed in this lecture here. So give me a second to clear the board, and I will bring the questions up. Okay, everyone, so here are the questions. There's going to be some math involved in some of these, and then I also have thrown in a theory question to make sure that you understand isotopes. So, how many hydrogen atoms are in 13.5 grams of water? Now you need to pay attention to the wording here. This says how many hydrogen atoms are in 13.5 grams of water, and you see your options there. You should logically think about the fact that 13.5 grams of water, that's a significant amount of water that you could hold in your hand. You could see it. So you should have a lot of hydrogen atoms associated with that, given how small atoms are. So those are the choices there. All right, now number 2, similar but different question. How many lithium atoms are in 1 mole of lithium nitride? That's Li3N. That's the substance. So how many lithium atoms are in 1 mole of Li3N? And I'll give you a warning here. A lot of students have a tendency to make this problem more complicated than it needs to be. So I'll just let you know that right off the top. All right, number 3. Bringing in a little of organic chemistry here, because you are expected to know organic chemistry for the MCATs. If you're struggling with this, then you need to go and check out some of the organic lectures, all right? Or at least the Lewis structure lectures. Now, what is the molar mass of aspirin? I've given you aspirin down here. This is an organic structure. Many of the hydrogens on this structure are going to be implied at certain positions. So what you need to do is you need to take this structure and you need to figure out what the molar mass of aspirin would be based on the structure that you see here. So this is similar to the problems that we did earlier, but I am not giving you the, C6H12O6 sort of formula. I'm not giving you the molecular formula. I'm giving you the structure, and you need to be able to determine it from that. Very reasonable question to ask. All right, and then number 4. We've got hydrogen has 3 isotopes, which include regular hydrogen, H1, deuterium, H2, and tritium, H3. Which statement is most accurate? And here are your options. Each isotope makes up 33% of the mass for hydrogen on the periodic table. H2 is likely the most abundant isotope. All 3 isotopes have differing proton amounts. H1 has no neutrons, while H2 and H3 have neutrons. So those are the options, and based on, again, I would encourage you to have a periodic table while you work through these. Based on those statements, that's what you're going to try to work with. So take a minute to copy these down. You can rewind it if you need to, go back through, make sure you have the questions set, and then I encourage you to practice these questions before you go through the walkthrough with me. So go ahead and prepare that, and then when you feel that you're satisfied with your answers or you need help walking through, come back and unpause it and we can go over them. Alright, so hopefully everybody has had a chance to work through these problems. So for the first one, states how many hydrogen atoms are in 13.5 grams of water. So what we're going to do here is we would take 13.5 grams. For the sake of space, I'm not going to write all the units here, but that would be grams of water. And then 1 mole of water is going to be 18.02 grams. And then I need to get into molecules of water if I want to discuss the atoms, the hydrogen atoms associated with the water. So what I would need to do is I would say 1 mole of water is going to have 6.022 times 10 to the 23rd water molecules. And I can't stop there because that's just going to give me water molecules. I then need to say that there are 2 hydrogen atoms in every 1 water molecule. And this, as long as I multiply that value by 2 at the end, should give me the answer. And it turns out that the answer is 9.02 times 10 to the 23rd. Now, you really would do the math and figure out what this is. You could try to take some process of elimination guesses, but there shouldn't be any of them that are necessarily smacking you right in the face as far as ones that you would eliminate here. And that's because I didn't give any obvious answers like 2 atoms, because in that case, if it were how many hydrogen atoms are in 13.5 grams of water, you would know there's more than 1 water molecule in that amount, so there should be more than 2 atoms, or something along the lines of that. Right? So the correct answer here is C. The one that you could potentially knock out is this one right here, because this is just Avogadro's number masquerading around as a large number there. So other than that, you would have to run through the proper numbers here, and you get C as the correct answer. And the key here, when I said pay attention to the wording, is that we're looking for hydrogen atoms, not water molecules. So you need to make sure that you take it one step further past the water molecules when you're doing that. The wording is very important when we're dealing with these problems. All right, now number 2, the one that a lot of students have trouble with and they start confusing. How many lithium atoms? The key here is that 1 mole is important. How many lithium atoms are in 1 mole of lithium nitride? So a lot of students try to struggle with this, and they say, you're not giving me grams, I need to go to the periodic table and get grams per mole so I can convert. So they start grabbing values off the periodic table. You're getting way too complicated while you're doing that. 1 mole is exactly 6.022 times 10 to the 23rd Li3N molecules. That's all you need to know there, because I made this exactly 1 mole. So 1 mole is exactly 6.022 times 10 to the 23rd molecules. You don't need the periodic table for this. So then all it says is how many lithium atoms are in 1 mole of this. Well, if there's 3 lithiums per molecule, and there's this many molecules, I need to take this number times 3. So I'm going to take Avogadro's number times 3. That's all you had to do for this problem. All right, and what you should end up with when you finish that is 1.81 times 10. Sorry, I had to look at my calculation there. 1.81 times 10 to the 24th lithium atoms. That's what the correct number should be. Again, Avogadro's number masquerading around here, and you could potentially use process of elimination to get rid of D, because you have fewer than Avogadro's number. So if I know this would take a little bit of thought, but if I realize that I have at least Avogadro's number worth of these molecules, then at the minimum I need to at least have that many lithiums, if not more. And it turns out there's more because it's 3 lithiums that are in there. And so when I am looking at this, the correct answer would be the 10 to the 24th answer, which is A. All right, now what is the molar mass of aspirin? In this case, you needed to go through and determine how many of each atom you had. So you can readily see that there's going to be 4 oxygens that are present. And then if you take a look at the carbons, you need to count every point. So here's 1, 2, and then you come here, this is 3, 4, 5, 6, 7, 8, 9. Okay, now don't get confused right there. That is not a carbon. All right, so you've got 9 for the carbons. And then if you come through again, you have to use your implied hydrogen. So there's 1, 2, 3 hydrogens that would be present there on the methyl group. Carbonyl wouldn't have any. The ring would have 1 here. This would be 2. This would be 3. This would be 4. And then don't forget, so there's 4 over here. Don't forget this one over here, which would be 5, because you do have that alcohol present there. So then you would have 5 for your hydrogens. So you would need to use the values here, 16 times, and again, mine, I have 2 decimal places out, so the examples I'm showing here only have 1 decimal place, but you should get a number that rounds close to one of these. So if we were to look at that, we would say this is 5, and then this is 9, and then this is 4. You add all of these together once you multiply them, and if you run it through your calculator, you should get something on the order of 180 grams per mole. And B would be the correct answer there if you were working with that. So hopefully everybody was okay with that. You need to be comfortable with organic structures when you're working with this. And that includes the condensed, the line bond structures, not with all the methyls drawn out, as CH3s and things like that. All right, so time for the theory question. Number 4, hydrogen has 3 isotopes, which include regular hydrogen, deuterium, which is H2, tritium, which is H3. Which statement is most accurate? Each isotope makes up 33% of the mass for hydrogen on the periodic table. Well, that's not true. If we look at the mass of hydrogen on the periodic table, it's 1 approximately. It's about 1 gram per mole, or 1 AMU for the hydrogen. So if that's the case, that means that the original hydrogen has a much larger weighting on this value than do the second and third options there, the deuterium and the tritium. So we would expect that H1 is much more abundant than H2 and H3. So that's going to cross out A. That wouldn't make sense, because if they were equally weighted, this value should be higher, all right, because each of them would be contributing a little bit more there. So B is also out, because it's saying that deuterium is likely the most abundant isotope. So in this one, we're saying, well, all of them are equally likely. You got a 33%, a 1/3 chance of finding any of them, right? And then here we're saying that the deuterium is the most abundant, meaning we would find deuterium more than the other two. Well, that's also not true. It's the H1 that's going to be the most abundant, right? Now, let's take a look at C and D. All 3 isotopes have differing proton amounts. This should automatically be out, because if we're saying that hydrogen has 3 isotopes, hydrogen is defined as hydrogen by the number of protons it has. A hydrogen has 1 proton. That's what makes it a hydrogen. If you suddenly have 2 protons or 3 protons, you've now become, in the case of 2, you've become helium. In the case of 3, you've become lithium. You're changing the chemical identity if you change the proton amount. So that wouldn't be good. So that must leave D, but let's see if D makes sense. H1 has no neutrons, while H2 and H3 have neutrons. Well, keep in mind the value here is the mass. So if hydrogen is H1, and that's its mass, and its atomic number on the periodic table is 1, that means that it has 1 proton, and its mass must be derived from that 1 proton. So it has no neutrons. That's correct. And then H2 and H3 must have neutrons. Well, that's also correct, because hydrogen, again, can only have 1 proton. So if it has 1 proton, but we find that the atomic mass is 2, then it must have 1 neutron in order to accomplish that. And for H3, if it's got 1 proton, again, because it's hydrogen, it then must have 2 neutrons in order to accomplish a mass of 3. So what we're really focused on here is that isotopes, okay, have varying neutrons, and specifically in this case, most of the isotopes you come across, they'll all have neutrons, but in this case, hydrogen is interesting because hydrogen does not have a neutron in its regular form, and then its isotopes do. So we are technically varying the number of neutrons. We're going from 0 to 1 to 2 when we're doing that. All right, so those are the questions. I'm going to clear this off, and then we will do a brief summary of everything we discussed and talked about here. So give me a second to clear off the questions, and I will bring up that summary. Okay, everybody, so here is the summary for the Mass, Moles, and Molecules lecture. First of all, we looked at the structure of atoms, and we noted the protons and the neutrons were in the nucleus, and the electrons were in the outer area. And what was important here is we said that atomic mass for any element was going to be obtained by adding the protons and the neutrons together. And so that was where we ended up coming up with atomic mass, and the proton and the neutron would each contribute an atomic mass unit. And we defined atomic mass unit along the way as being exactly 1/12 the mass of a carbon-12 atom. That is what defined an atomic mass unit. And then we said, protons and neutrons each give an atomic mass unit. But that's our official definition there, 1/12 of a carbon-12 atom's mass. So then we were looking at the periodic table, and we said that with the periodic table, mass is going to come from the collection of isotopes, because we saw that example with copper that didn't quite make sense where we saw fractions of a neutron. And we could explain that by taking a look at the fact that there are multiple isotopes of copper, or any other atom that we were looking at, and that the masses found on the periodic table really come from the weighted natural abundance of each of those isotopes when we add them together. And that is what we can attribute the molar masses to when we start using the periodic table. So remember, isotopes differ in their neutron makeup, never in their proton makeup. And we saw some of that in the theory question. I know I mentioned it earlier in the lecture. Protons, again, protons give the identity of the element, and that is known as the atomic number. And the neutrons can vary. Those can be creating different isotopes, and certainly you can have different masses. One carbon can weigh more than another carbon, a 14 versus a 12, but that's due to neutrons. That is not due to additional protons, and you have to remember that, okay, because protons also contribute to the mass, but those are not the ones that are going to be changing when you're dealing with isotopes. And then we talked about a mole. And a mole of anything, it doesn't matter what you're picking out, similar to the example we used with a dozen, a mole of anything is 6.022 times 10 to the 23rd units. That's Avogadro's number. And we stated this specifically as the number of carbon atoms in exactly 12 grams of carbon-12 isotope. So we're using carbon-12 to kind of standardize a lot of this here. But the key concept to the mole is that anything that is exactly 1 mole is 6.022 times 10 to the 23rd units. And those tend to be very small units that we're talking about. So molar mass, when we get ready to start converting grams and moles back and forth, molar mass, okay, of a substance can be obtained by adding the masses of all the atoms involved. So we did that with water and glucose and acetic acid. Then you did it with aspirin in that final question that we were working with. And the molar mass is obtained simply by summing those up. The unit here is grams per mole. So when you utilize the periodic table and you add all that up, that is the number of grams per mole of the substance you're working with, or the atoms you're working with. And then finally, we looked at converting into atoms or particles, and Avogadro's number is utilized for that. We would use Avogadro's number once we've obtained moles. Remember, moles is that central unit. So you can go from grams to moles and moles to grams. You can go from moles to atoms and atoms to moles, but you can't go from grams to atoms and atoms to grams. You need moles in between there. So Avogadro's number can be used once the number of moles is obtained, or it might be given to you in a problem. And then you can find smaller particles such as atoms, molecules. You could even use it to find number of electrons. If you knew the number of electrons associated with a particular atom and you had a mole of those atoms, or any type of small particle is acceptable there. So that concludes the summary for mass, moles, and molecules. Again, keep in mind that this is really a primer for getting ready to do some stoichiometry, which is what some of the future lectures will encompass here, and you will need this as a background skill in order to start finding, for instance, the limiting reactant or the theoretical yield in any given situation. So hopefully everybody found this helpful, and we thank you very much for learning with us, and we will see you guys for future lectures.